of course. Okay, now the next family there that we're going to have a look at are the aldehydes. The functional group of the aldehydes, C double bond O and a H. Remember your definition of a functional group: atoms or group of atoms that are responsible for the characteristic properties. So this is the functional group of aldehydes. So if I was to change that to ethanal, there's my ethanal. Now what do I notice about aldehydes? I notice that they are, this is tetrahedral carbon. So how do I know that that's a tetrahedral carbon? 4 single bonds. This is a planar carbon, okay, because it contains the double bond, all right. So they're not hydrocarbons, obviously, because they contain oxygen as well, all right. So you have the C double bond O and the OH here. Now, this is a polar bond here, okay. So that's going to affect the properties of aldehydes, okay. So if I draw a neighbouring aldehyde here, C double bond O and a H, and if I just put in the double bond O and the carbon is slightly positive, so that's that. What's the type of intermolecular force I can have between the slightly negative oxygen and the slightly positive carbon? Dipole, dipole. So I have dipole, dipole forces between aldehydes. Why can't I have hydrogen bonding there now? You have oxygen bonded to carbon, not to hydrogen. So you can't have hydrogen bonding there. Now we would have said that dipole-dipole forces were stronger than van der Waals but weaker than hydrogen bonds. So boiling points of aldehydes would be in the middle, between alkanes, alkenes and alkynes, but lower than the alcohols. Okay, now what about if you put something like ethanal into water? Would there be any interaction between the ethanal and the water? Well, remember now, this is slightly positive, this is slightly hydrogen. And if I just draw a couple of water molecules, so this is solubility now. Don't mix up boiling point. What determines boiling point is the type of intermolecular force between the molecules and the size of the molecule. What determines solubility is would there be an interaction, if you like, between the molecule of ethanal and the water. Now, water, remember, is a polar solvent, so slightly positive hydrogens, slightly negative oxygens. Now look, you do have some interaction there. Interaction between the slightly positive oxygen of the ethanal and, the slightly negative oxygen of the ethanal and the slightly positive hydrogen of the water. Okay, and you would have interaction between the positive carbon and the slightly negative oxygen. Now, you can call these hydrogen bonds because you do have oxygen bonded to hydrogen there. So the interaction there between the water and the ethanal will sort of will break up the ethanal molecule. So yes, ethanal is soluble in water. Again, C1 to C3 soluble. After that, your solubility is decreasing as the length of the carbon chain increases. Okay, methanal was the thing we learned the use of. Methanal is used to preserve specimens as an embalming fluid. And the other thing, actually, as I'm at it, this aromatic compounds we would have spoken about before, but there's your benzaldehyde, and benzaldehyde is found in almonds, remember, okay, would have had that use for that. Now, ketones then is the next thing. Now remember, for a ketone, the functional group's in the middle. Okay, so that would be your first member of the ketones is propan-ON. Functional group there, C double bond O. What you notice about it, it's also polar, isn't it? Now, in terms of tetrahedral carbons, that's a tetrahedral carbon, that's a tetrahedral carbon, but this is a planar carbon here. All right? So that's your ketone. First member, propanone and butanone would be the main ones that they would use there in your exams. Propanone is acetone, nail varnish remover, it would be the main use for that, or a butanone, or used as an organic solvent, that sort of thing. Okay, now in terms of properties of the ketones, right, so double bond O, right, so if I was to draw, this is one propan-ON, okay, and I was to draw a neighbouring propan-ON here, okay. Now look at the polarity, the slightly negative oxygen, slightly positive carbon, slightly positive, slightly negative. So what happens here, you do have interaction between the slightly negative of one propan-ON and the slightly positive carbon of the neighbouring propan-ON. Now what type of interaction is that? Dipole forces, okay? Again, you can't have hydrogen bonding there because you don't have oxygen bonded to hydrogen. You have oxygen bonded to carbon. So dipole forces. So what would we say about ketones? Ketones would have slightly higher boiling points than alkanes, alkenes, alkynes, but they would have lower boiling points than the alcohols would, okay? Because I remember alcohols can have hydrogen bonding. So then if you put something like propanone into water, okay, So they're the hydrogens there. So again, we'll just label the polar bond. So you'd have to check first to see, does the molecule have a polar bond? And if I drew another one, or sorry, no, it is water I'm drawing. Sorry, hang on now. So just, see. So it is water I'm drawing here. So I'll draw a molecule of water there, slightly negative, slightly positive, slightly positive. So look, you do have an interaction there between the slightly positive carbon and slightly negative oxygen of the water and here. Now, these are hydrogen bonds. I can call these hydrogen bonds because you do have hydrogen bonded to oxygen in the water. So there are hydrogen bonds occurring between the propanone and the water, pulling the propanone molecule. So propanone would be soluble in water, but again, anything greater than C3, then the solubility decreases as the length of the carbon chain increases. Okay. Then the next thing would be the carboxylic acids. Okay, so carboxylic acids have that functional group, C double bond O and OH. Now again, look, what do you notice here? You notice actually here that you have two polar bonds. All right, so if you have something like ethanoic acid, and if you have a neighboring ethanoic acid here, okay, OH and double bond O, and I'm going to use the yellow there now for the charges there. Okay, look and what you can do, right? So you can have slightly negative oxygen, slightly positive hydrogen there, and the slightly negative oxygen, slightly positive hydrogen there. So you can actually have two hydrogen bonds per molecule of acid. That's what you call a dimer. So yes, they're hydrogen bonding here now between acid molecules, but one molecule and the next can actually set up two. Whereas with the alcohol, you could actually only have one hydrogen bond per molecule, okay? So just to be clear now, so about boiling points. We would have put them in order as well in that A3 sheet that I'm talking about. Alkanes, alkenes, alkynes, that would be they'd have the lowest boiling points. Then you'd have aldehydes and ketones, okay? Then you'd have alcohols, and then finally you'd have carboxylic acids. Actually, esters go in there too. We didn't talk about esters yet. So in terms of boiling point increases, you go up like that. Why? Because van der Waals are the type of intermolecular force you can have between these. Dipole-dipoles between aldehydes, ketones and esters. Hydrogen bonding between alcohols, but dimers. You need to mention the word dimer there if you're asked to explain the high boiling point of alcohols. Of acids. They have the highest boiling points. Now, methanoic acid found in stings of nettles and ants. Ethanoic acid uses would be used to make vinegar. Now watch the propanoic acid and the butanoic acid. They've been coming up a bit. Propanoic acid, bucanoic, and their salts, by the way, used in food preservatives, that sort of thing. Okay, now what about if you put a molecule of ethanoic acid into water? So let me draw a water molecule here. Would you have that's a negative. Would you have would you have any interactions? Well, you would. Okay, because you have polar bonds here in the acid molecule, you will have interaction between that and the water. Like if I drew another water molecule up here, there's slightly positive interactions there. Type of interactions, they're hydrogen bonds. So your question is, would ethanoic acid be soluble in water? Yes, it would, because of the hydrogen bonding that occurs between the ethanoic acid and the water molecules. Again, anything longer than propanoic acid, the solubility starts to decrease because the length of the carbon, CH, the non-polar part is starting to increase. Okay. Now, finally, then you have esters. Now, functional group of esters. You have the C. Okay. Bond O, but you have the O. Do you remember? So you have the oxygen bridge there linking. Sorry, I shouldn't have had that there at all, actually. So you have the oxygen bridge linking one carbon to the next. Okay. Remember we said that this is the part of the ester that would have come from the acid, and this bit would have come from the alcohol that was used to make the ester. Okay. Planar carbon there when you see the C double bond O because of the double bond. This carbon would be tetrahedral because of 4 single bonds. Remember that when you're forming esters, you need an acid and an alcohol making the ester in the water. And remember uses of esters. They're fruity smells. Remember we made some test tube esters in school. So fruity smells are used for flavourings, used as a solvent for making glue, for making soap, those sort of things. Okay, now if I just draw this would be oxygen. So there's one ester there. Now, what would we call that? we asterisk the carbon that came from the acid, okay? So that's acid was ethanoic acid, so it's called ethanoate. And what's in front of the oxygen bridge that's linking the acid to the alcohol part? A CH3, so that's a methyl, isn't it? So that ester there is methyl ethanoate. So you asterisk the carbon that came from the acid. This bit is the acid part, so ethanoic acid was used, so it's ethanoate, and then methyl in front. Now, what about boiling points? Just to recap on that, look at your polar bond here, slightly negative, slightly positive. So you can have dipole forces between esters. So their boiling points would be similar to the aldehydes and the ketones. Again, if I put that into water, you would have some interaction between the water molecules. So again, C1 to C3 be soluble in water. After that, the esters, their solubility would decrease as the length of the carbon chain increased.